Hello everyone, in this video we'll be solving problem 110, balanced binary tree. The problem statement is, given a binary tree, we need to determine if it height balanced or not. Height balanced means that the depth of the left leg of a node is equals to the right leg, or the difference should not be greater than 1. If we look at example number 1, for node 3, on the left hand side the depth is 1. But on the right hand side the depth is 2. Because the difference is still 1 and not greater than that, it is a valid height balance node. Similarly, we need to calculate the height balance aspect for each node in the tree. It is possible that the root node may be height balanced, but one of its legs is not. If we take this as an example, for the root node, the left leg depth is 3 and the right leg is 4, which makes it a height balanced node. But if we look at individual nodes within the left and the right legs, but if we calculate the same for individual nodes on the left and the right legs, they may not be. For example, this node have the depth of 2 on its left, but there are no nodes on the right. So this is not a height balanced node. So we need to make sure that all of the nodes in the binary tree are height balanced. Similar to the example that we just talked about, node 1 have the depth on the left leg as 3, but on the right side it's only 1, which makes it an invalid or not a height balanced tree. I hope you were able to understand the problem statement and what exactly does height balanced mean. Now let's talk about how we can solve this problem. For a height balanced tree, for each node, we need to make sure that we are aware of the depth of all the nodes underneath it. For example, when we are calculating the height balanced or checking the status for node 7, we need to keep track of the depth for its left and its right leg. Make sure the difference is not greater than 1, and if it is, then throw an error. To solve this problem, we'll use DFS approach because we want to start from the last node in the tree. So we'll start from root node and go to its left leg until we know that a particular node does not have a left and a right leg. And this becomes the starting point. So for this node, the difference of the depth of left and right is going to be 0 because there are no nodes. So we'll keep the diff as 0 or the depth as 0. Now when we are going back to its parent, the depth should be 1. Now we'll do the same calculation for the right. So when we go to the right node, which is 5, similar to what we did for 4, we'll calculate its left and right because there are none. So its depth is 0. And when we are returning back, the depth should be incremented. So now here, the dr should be 1. Comparing the difference is 0, so which means this is a valid height balanced node so far. And so are 4 and 5. So after processing node 2, we'll go to its parent and we'll record the depth. So dl, depth of left leg, is 2. And now we'll go to its right leg, which is 3. We'll continue to go into the deepest node using DFS. So now we are at node 6. Just like we did for node 4 and 5 or 6, its corresponding depth will be 0. We'll move back to node 3. DL will be 1. Now it calculate for 7. For 7, it's a slightly different scenario. We do have a left leg. So we'll go to the left leg, 8. 8 is similar to 6, 4 and 5. So its depth will be 0. We'll move up. So for 7, DL will be 1, but DR will be 0. Difference is 1, so we'll still continue the iteration. We'll go up to node 3. DR here will be 2 because DL or node 7 is already having a depth of 1. Comparing DR and DL, the difference is 1, which is still valid. So we'll go up to node 1, dr will become 3. As we are taking the maximum between dl and dr, so the depth on the right leg for node 1 is 3, but for the left leg it is 2. If we look at the difference, it is still 1, which is valid, so we'll return true. If we had one more leg here to 8, let's say node 9, the calculations would be different and the dr for node 1 would have become 4. And with the difference being 2, we should be returning false. With this solution, our time complexity is O of n, where n is the total number of nodes in the given tree, and the space complexity is O of 1, as we are only maintaining the depth of left and the right leg at each node. I hope you were able to understand this explanation. Let me show you how we can implement this using C#. Let me show you how we can implement this using C#. For the implementation, I have created this utility method called DFS passing the tree node. If the node is null, then I simply return 0. If you look at the lower part of the code, where we are actually comparing the left and the right height, if the difference is greater than 2, we are returning -1. We are using -1 to determine that we don't need to resume or continue the iteration. We can simply exit out because we have found one node which is not a height balance node. So we are checking if the left height that we have calculated using recursion is it equal to -1. If it is, we are simply returning -1 here and stopping the iteration. Just like what we did for left height or left node, we do the same for right node. If we get a valid values for left and the right legs of the node, then we are calculating the absolute difference, and if the difference is less than 2, we are returning the maximum height of that particular node, which is math.max of the left height and the right height, and then incrementing it by 1 because we need to also add the current node as a height. If the difference is greater than or equal to 2, we return -1, which indicates that we need to exit out of the iteration. This solution, when submitted on LeetCode, beats 100% of the submissions made so far in terms of time complexity, and in terms of space complexity, it beats nearly 60% of the submissions. Thank you for watching this video. I hope you were able to understand this solution. The link to the source code is available in the description below. Feel free to check that out, and I will see you in the next one. Thank you.